Thanks everyone for turning up, and it's a great pleasure to present to you Professor Gordan Jelenic from University of Rijeka as a part of UCD Center for Mechanics series of talks, which is also supported by the Science Foundation Ireland Nexus project. So, Gordan.
Thank you very much. Thank you, Gordan, and good afternoon to everyone. I was here as an external examiner to Giovanni's PhD thesis today, so on the way, we agreed that I would present you some of the work that we do. I'm coming from the University of Rijeka in Croatia, on the Mediterranean coast, and what I currently do with my group is really research on the cost-of-arts continuum, and we are running a project under the auspices of the Croatian Science Foundation, and as a part of that project, really I looked a little closer into the topic that I'm presenting you today, which is large curvature pure bending into the hyperelasticity, with a specific emphasis on some properties that I find interesting, and some of them already reported, some of them not. So far as the project is concerned, oops, let me just see how this works on. Oh, here it is. Okay, that's fine. Okay. So this is the group that works with me. Within this project, these are my colleagues, Gordan, Edita, Sara, Laura, Eddie. I have to find the right pressure with which to press the key here, because it doesn't seem to be responding to any pressure. This is what we are as a group, and the problem that okay.
Cursor is maybe this away on top. What?
The cursor is moving, so we need to do it in a slide. So,
how do I do it? I have no idea.
Yeah.
Maybe it's not necessary.
No, it's fine. It's
I
fine.
think it's. Oh. Fine, looks better. Thanks. Okay. So the topic that I'm presenting today to you is something that is very classic, very well known, something that we meet at the very beginning of our engineering education, but considered in a slightly or largely different setting than what we normally do. We're talking about bending. We're talking about pure bending. Okay, we're talking about the situation in which a specimen is bent into a part of a circular arch. But now, what we don't consider it the lens of the beam theory. We consider it with the lens of the continuum theory, and see what happens there, and what happens if the curvature is large. And there are many interesting phenomena that happen. So the question that we are posing to ourselves here is, for what class of hyperelastic isotropic materials does the solution to this problem exist? And when I say the solution, I mean some sort of an analytical solution. Okay. Right. So as I said, this is a classic problem, even in this continuum setting, obviously. And the oldest traces that I could find was due to Seth in 1935. And then after the Second World War, Rivlin carried on with that. And then Ogden, obviously, was in anything related to hyperelasticity present. Then there is this Russian guy, Luria, to whom I would return later. These two guys extended the solution to some particular class of materials, as did Bruns at the University of Darmstadt in Germany. And finally, one of his collaborators, Xiao, carried on and generalized this solution to a wide class of problems. But as I will try to present to you, not as wide as is actually possible. So just to set the scene, let me show what Luria did. Okay, so he considered the setting in which the strain measures to be taken and put into a constitutive relationships with the stresses are the so-called Biot strain measures. Okay, the Biot strain is in fact the first thing that we think about when we think about how to train to nonlinear analysis. So we have an extended length, we have the original length, we subtract the two, divide by the original length, that's our Biot strain. So exactly as we do in linear analysis, but that's the generalization to nonlinear analysis. In our particular setting, we have a longitudinal strain and a transversal strain. And they both depend on this R, which is the value from the center of curvature to a particular point in the specimen. Rho is the radius of curvature of the undeformed fiber in the deformed state. Okay. So these are the strains that we take, and correlated to those strains are the so-called Biot stresses. And here we consider the relationship between the two standard materials. So this is what we did. Okay, this would be the equilibrium equation in the tensor form, which receive a scalar expression, which I don't have here. What is important to say is that this is the extension of the standard engineering strain to nonlinear analysis. This is exactly the same as it is in linear analysis. This is the nonlinear equilibrium equation. This is what makes the problem nonlinear. So the constitutive part is no further complications with respect to the linear analysis. Now, in Luria's case, the problem boils down to a simple differential equation, okay, for the position of the particle in the deformed state, depending on the radius of curvature of the undeformed fiber and depending on the n, which is Poisson's ratio. It's very simple. And this is the solution as a consequence of this differential equation, and these would be the stresses as the consequence of this differential equation. Now compare it with the linear analysis. We would obtain the linear analysis if we expand these nonlinear functions into Taylor series. Hyperbolic sine would turn into this pattern. Hyperbolic cos would turn into 1. Is that the stresses are really linearly changing across the cross-section of the beam. H2, I forgot to say, is the coordinate along the cross-section of the beam in this vertical direction. This is the longitudinal stress. This is the through the thickness stress. And in linear, this is 1, the parentheses disappear, and we obtain 0. So this is what we have in linear, but not in nonlinear analysis. Okay. Now, as a result, if you take a beam of 10, so this would be the deformed state that we would obtain at a certain amount of the radius of curvature, which is roughly 3 times 3 times larger than the height of the beam. Okay, if we increase the curvature twice, obviously we obtain twice the bigger angle. And this does not look at all different from what we would obtain in standard nonlinear beam theory, as Shivani knows very well. Okay, but now if you want to make it thicker, so I'm just really taking into the extremes, and I'm taking a situation in which the length is wide, so you could hardly call it a beam. Okay, for a certain radius of curvature, this would be the you can see certain shrinkage in the cross-sectional area as a consequence of these through-the-thickness stresses, which exist in one nonlinear analysis. They do not exist in linear analysis. This would be the linear solution. The point of the synchronical line would move only vertically. It would not move horizontally. Horizontally would move the edges of the cross-section equally to the left and the right, which would really distortion, which makes really the linear solution inapplicable. If we increase the curvature, we also increase the amount of this cross-sectional shrinkage more. So this would be the continuous solution to our problem. Now, what is interesting is also that if we look into the stresses, so this is the diagram that shows how longitudinal stresses change over the cross-section. So this is the, and in linear analysis, we have the linear distribution of the stresses. As the curvature increases, the linear, we have this departure distribution. And more importantly, we have through the thickness stresses, but in the middle, they can get certain value, which is now given in proportion to the amount of the loading that we produce, the amount of the surface loading that we produce, the bending moment at the edges. Okay, so if this is the same, so basically for the largest curvature, the stresses would get nearly the same value as the amount of the pressure that is applied on top or bottom of the cross section. Okay, now this is what we did. Okay? He did it for this type of material, for the material in which linear elasticity existed between the built strains and the built stresses. That's one way of presenting it. There are other ways. This is the very popular Summerland-Kirchhoff's material, in which linear elastic relationship exists between green Lagrange strains and energy conjugate stresses, which in this case are second-order Kirchhoffs. And the green Lagrange strains are defined as this, as a function of this right stretch tensor, which is the component in the deformation gradient obtained. Now, I'm stressing this because in all the materials here, we will be seeing very similar expression for the strains. But these are just different choices that we can take in nonlinear analysis for our strains. So this would be the so-called Almansis strain, at least one of the two versions that exist for the Almansis strains. So we can work out some energy conjugate stresses, which are not the Cauchy stresses, despite the fact that very often in literature you can find that claim, but there exists an energy conjugate stress tensor to the Almansis strain tensor, and we can work out a material in which the relationship between and this is again one popular material called Henke's material, in which we have logarithmic strains. Okay, and the corresponding stresses, which are just so-called rotated Kirchhoff stresses. Now, what I want to say from here is that all of these different strains can in fact be written in this way. So for a different C, if C is 1, it's Beer stress, Beer strain. If C is 2, it's Lagrange's. If it's -2, then it's Almansis strain. If it's 0, then it's Henke's logarithmic strain. And so all of them can be written like this. And even the last one, the Henke strain, for which C is equal to 0, value of this expression here. Now, the corresponding stresses, without any derivation, could be written like this. Okay? So we have a certain to have a stretch tensor to a certain power, we have the rotation stress and the corresponding stress to any chosen strain tensor can be written like this. Now, with this in hand, we can write our equilibrium equation like that. And if we use the same linear expression between the strains and the stresses, whichever they are, because they can be anything from that family, then we have our positive relationship. Okay, so this is really the generalization of what Luria did to the whole family of the so-called Set-Hill family of materials. Set is actually the guy who first came up with this general expression for this. Hill is the one who said that it is important to start from the energy if you wish to attach a particular stress tensor to a chosen strain tensor. Okay, so they are called Set-Hill materials, and these would be like the class of this material that really have the linear correspondence between the strains and the stresses, which we choose on our own. Right. In a general case, then we can write our longitudinal strains or our transversal strains, or any. And if C happens to be equal to 0, then again we have some limiting value. So this would be the relationship between our kinematics and our chosen strains. I give it to you without any particular derivation and without any particular going into detail. I just want to stress the difference between the differential equation of the problem set up for the whole class of the materials and contrast it to the one that was obtained by Luria for just the material in which we have the linear relationship between the Biot strains and the Biot stresses. So the difference in complexity is more than obvious. However, despite that, and that's the first important point that I want to make, we can relate some of the parts here. Strains. Write whole of this equation in terms of strains only. When we do that, we obtain this result here, which says that we have some expression in strains differentiated with respect to the through the thickness coordinate, which is equal to 0. And this really means that for the whole class of materials, this differential equation has a first integral. Well, is simply the expression within the braces. So it has to remain constant because its derivative is equal to 0. Okay, and how do we compute it? We compute it very easily. So it's constant through the cross section, which means that it's same at the same place, including the top and the bottom. And on the top and the bottom, we know that we do not have any through the thickness stresses, which means that the longitudinal and the transversal strains are related. Just work in this relationship, we obtain a very simple expression for this constant, this first integral of equilibrium, which along the way shows us that the strains on the top print only in their side. Okay. Now, so the first important thing that I wanted to make is that there exists a first integral of equilibrium. Second important thing that I'm making now is that this first integral of equilibrium is an expression in which longitudinal strains take place in a way which is at most a quadratic equation, either in one or in the other. So we can solve this quadratic equation and express one in terms of the other. So this is what I do here. And I express the through the thickness strain in terms of the longitudinal strain, again, depending on the C. Why is that important? It is important because it depends only on R dash, on the change of the position in the polar coordinate system or a particular point in the cross-section. Whereas the longitudinal strain depends only on R. So if we can express in terms of the longitudinal strain, we can express R dash in terms of R. And if we do that, then we have a differential equation. That's really that poses the solution, and this solution is made by this is the solution by Xiao. I actually derived it myself, only to find out that it was derived by him some 10 years ago. I'm sorry, that's not very, but it is what it is. So this is the result that Xiao actually presented in 2011. Right. Oops. Okay, right. So since we have this differential equation, obviously we can, and you remember, just in terms of R, which is our unknown function. So we have derivative of the function equal to function of R, and then obviously we can obtain the position. We can obtain the position as an integral of dr over this function. So this is the result. This is the result as obtained by Xiao. Now, let me show you some numbers. Okay. I'd like to show you what happens if we give a particular stretch to the bottom fiber into what happens with the strain at that same fiber, depending on the chosen C, which means on the chosen definition of R strains. Okay. So here, I'm presenting the results in which I show what is the amount of the strain depending on C, which remember is a particular material, green Lagrange, logarithmic amounts for a given stretch, 1%, 10%, 40%, 100%. Okay. So for very, very small stretches, as we know very well, strains do not change much. The difference is barely visible. As we increase the number of stretching to say 40%, then we see an obvious difference in the amount of the corresponding strains. And if we go it even further, then the difference becomes very, very, very visible. Okay. Now, if we wish to see what happens, the strains on the opposite side would be equal in magnitude, as we said earlier, just different in the sign. Now, if we wish to look into what happens with the stretches on the other side, so we bent our beam, we extended the bottom fiber, we squashed top fiber. So this graph shows the amount of squashing of the top fiber. Again, depending on C. Green Lagrange, weird logarithmic amounts. Okay? Again, for 1%, 10%, 40%, 100% of stretching of the bottom fiber. And now we see one interesting thing here, that for certain materials, like billets or Saint-Venant-Kirchhoffs. We can't do that indefinitely. If we stretch our bottom fiber too much, we will squash our top fiber into zero. Up to a certain amount of stretching can we obtain the results for this range. And remember, C can run from minus infinity to plus infinity. So it means that there exist materials for which we cannot really obtain a physically viable solution. And this is well known. Okay? All the materials with positive C do not possess sufficient energy growth in their energy density to prevent singularities from happening in the stretch tensor. This is why we sometimes say that Green-Lagrange strains are not suitable for large strain analysis. Because in large strain analysis, simply we may not obtain a physically viable solution. But it's not only Green-Lagrange strain, it's all the strains with the positive C. It just depends when will it happen. And my final graph is showing what would be the amount of the radius of curvature, again, for the given stretch. Depending on the material, always depending on the material. Here, we show that for 1% of stretching, the difference in the radius of curvature is what? About 1%. But if it comes to, say, 40%, then it's much larger. And even for 10% of stretching, which is the gray line here, we see the difference of roughly 10%. Meaning that for a specimen of certain length, say 5 times larger than the height of the beam, 10% edge extension in pure bending in different materials bends the specimen in the range of plus or minus 10%. What does it in principle mean? It means that perhaps a suitable parameter is found to match the experimental measurement, characterize a material. And so this is something that I presented last year at the ECOMOS Congress in Oslo. And then a question was asked, do I really think it's possible that you can describe such a complex behavior just adding one single parameter? That I have no idea at all. I didn't try it. I know what an attempt I can make to try it, but I don't have an answer. Now this question actually started me thinking about something, and this is what I'm going to present next. Because the results that I showed you here, in terms of the existence of the first integral and the extend beyond perceptive materials. This is something that is currently under progress. This is something I'm working on now, something that I plan to publish soon, but it has not been published yet. So we are talking now the general class of hyperelastic, sometimes called green elastic materials. So the materials for which we know that we have a strain energy density function as some fundamental quantity that is really beyond the fact that we have elastic behavior in the sense of the absence of the cause of the deformation actually knows the deformation itself. So what is important that in hyperelastic materials, there exists a strain energy density function. We sometimes take it for granted, but if you want to be very, very strict, we can say that stresses and strength may be linear, okay, and elastic, without actually necessitating existence of the strain energy. But if the strain energy function does exist, okay. So in the hyperelastic materials, the strain energy density exists, and then the stresses are obtained from there. So in case of the field stresses, this is how we obtain them. And in our particular case, where we know longitudinal strain and the thickness strain, then obviously the corresponding stress can be obtained in this way here. Now, if you write down our equilibrium equation in terms of the strain density function rather than the stresses itself, then it turns out to be this. Now, what is interesting here is that both of these coefficients, 1 over rho, and this differential operator can be written in terms of stretches or their derivatives. So this equation can be written in this way here. Why? First term, second term, last term. And the two in between are equal and opposite. But if we group them differently, we realize that both of them are actually some total differential, either of the strain energy density or whatever is here within the parentheses, divided by dr. Meaning, may be expressed in this form here. Now remember, for the set field formula of materials, the long thing within the braces had a dash and was equal to, this is the same thing here. Just the principle is much more general. So it's not only the set field materials, it's the wider class of hyperelastic materials that still possesses the first integral equilibrium. And this is the first integral equilibrium. Okay? This has to be a constant, and we can easily compute this constant. Because at the top and the bottom, we know certain relationships where the thickness stresses are 0, which enables us to compute it. Okay. So basically, this is something that is valid in equilibrium of a pure bending problem for any hyperelastic material. We're really talking about the fact that certain value is not being changed as we move across the cross-section. It's observed. And as we know in dynamics, the first integral of the motion always means either energy is conserved or momenta are conserved. Okay, so it's the same thing here. Okay, first integral of the motion is certain conservation. Right. This law here may be extended to generalized plane strain problems, in which case we don't have the lateral strain which is prevented as it is here. And I forgot to say that it's a plane strain problem here that we are considering. Okay, but it can be in a unique manner applied. That's called generalized plane strain. It can be applied to the problems of constant initial curvature. It can be applied to the precise material that I mentioned at the beginning. All of this is possible in within this framework. Okay, we're talking about the conservation property. It's instructive to note that this thing here that occurred as the second term in our first integral is in fact a particular stress component, so-called Kirchhoff stress component. So there is a clear physical, verbal explanation of this conservation law that says that in pure bending, in pure plane strain bending, the transversal Kirchhoff stress at any point in the specimen is equal to the strain energy at that point relative to the strain energy at the edge. Very simple. Okay. Or you can write this. Now, remember before that I said there are two important points to make. One is that exists a first integral of motion. And the second is what needs to be respected to obtain integrability. So we're talking about the second thing now here. Okay. Since the strain energy, again, is a function of both stretches, and they themselves are function of either the position, which is R unknown, or its derivative, the first integral of equilibrium here is an first order differential equation relates unknown function to its derivative, possibly in a highly nonlinear manner. But this is the relationship that exists. Okay, and the problem will become integrable for a reduced class of these problems for which this first integral may be expressed in this way. So if we are able to express our derivative of R with respect to through the thickness coordinate in terms of any, however complicated it may be, a function of R, then the problem becomes integrable. When I say integrable, I mean it in a mathematical sense of the word, meaning of integral of something, irrespective of whether this something can be expressed in terms of analytic functions or not. Like in Kepler's problem, for instance, okay, which is integrable, but it's not expressible in terms of analytic functions. Now, in that case, this is the solution, and this is what I just mentioned. So whether we know the result of that or not, the problem is integrable. What else can we say about that? Sorry. Oh, yeah. Here?
Yeah.
Yes. Okay, let's try it. Right. So the question is, which strain energy densities will make the problem integrable? We know that the first integral always exists. Whether this means that the actual problem is integrable or not is not immediately here contained within the existence of the first integral. What is it that makes a particular strain energy integrable? Okay. For the set Hill family of materials, and they are materials which satisfy such a strain energy density, the first integral of equilibrium simply turned out to be a quadratic equation, which enabled explicit integrable form. Now, what we know is that cubic and quartic polynomials may also be solved in terms of radicals, which means that they can be analytically expressed. There exist formulas for the cubics and for the quartics, which give an explicit solution. Okay. Now, all strain energy densities for which the first integral of equilibrium turns out to be a polynomial of order not larger than 4, then provide an integrable solution. And now, let me show you an example. Okay. Gordan's family of materials. This is a general expression. You remember Ogden's a strain energy density expressed in terms of 3 stretches. This one is equal to 1 in our case, but this is the general expression. Risen to certain power. And given a sum thereof. So we can run up to any number here above the sun sign that we wish. This is a material from within the Ogden family. Now, in our case, set this upper limit either 2p plus r equals 4 or q plus r equals 4. Oh, that will be derived from here. Remember, phi minus lambda 2 derivative of phi with respect to lambda equals the amount at the edges becomes a 40 polynomial, which means that lambda 2 may be expressed in terms of lambda 1, which in terms mean that R dash may be expressed in terms of R. That's much simpler. Quadratic equation, this is lambda 2 in terms of lambda 1, is obtained with the upper limit in the above sum set to p plus r equals 2 and q plus r equals 2. Such a material will still leave us 14 parameters to characterize it. This one, much more. So in principle, we have an analytical solution to a very complex material. And we can now think back to whether we can use a certain experimental measurement to see whether it really fits with our material. Now, this is a facility that exists. You may know about this. It's a facility that exists at the University of Saarbrücken in Germany, from the Fraunhofer Institute in Kaiserslautern, from where the colleague Vanessa Jelenic arrives, collaborate very, very closely. So what we're trying to do, we're trying to establish a contact with them and see whether we can run some experiments that may possibly see the usefulness of these solutions. So what does this experiment do? You see, there is a little specimen that can be put between those clamps, which can then be rotated up to 90 degrees. Okay? So in fact, it can be started from minus 90 degrees and rotated up to the 90 degrees. And remember, this solution may be generalized to initially curved beams. So in fact, we can start with a quarter arch, okay, and bend it into an opposite quarter arch. Huge bending. And we have now available a material with a vast number of material parameters for which we can actually see whether there is some correspondence between the theory and the experiment. So this is what my group actually is planning to do for the future. Yeah, let me just work it out. So what we saw is that in large strain 2D pure bending hyperelastic class of materials, there always exists a first integral of equilibrium if we're talking about the large curvature bending in plane strain state. And this first integral of motion really says that the difference between the transversal Kirchhoff stress and the strain energy density at any chosen point is equal as the strain energy density at the edge of the specimen. Okay. This first integral of equilibrium relates the two strain components, radial and circumferential, possibly in a very, very nonlinear manner. But if this first integral is a polynomial of order not larger than 4, then the problem will become integral. A large number of the materials will satisfy this requirement. Not obviously, because we cannot run the problem to the polynomial above the order of 4. But as we saw, if you stay at the order of 4, we still have a material with 55 parameters available. Okay. And then the large curvature bending tests will enable detection of these extra parameters in our current integrals. Which may possibly describe the observed behavior. Right. So this is what I presented for you today. Thank you very much.